Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIWA campus. Let's start with the lecture contents. In this video, we will discuss what are even and odd signals and how can we classify the given signal whether it is even or odd. The other is the decomposition of a signal. What does it mean that? For example, if you have a signal x of t, then you can decompose that signal into either into the this x of t signal into even combination of even and odd signal. So any signal continuous or discrete, we can express them as the combination of an even and odd signal. So we will learn this concept here as well. The last one which we will discuss will be the real and the complex exponentials. So these are some kinds of signals which we have to know because in future chapters we will use this concept. So if we don't know, then it will cause some problem for us. Let's start with the concept of even and odd signals. So what are even signals? For a continuous time signal x of t, it is called even. If you just put the time reverse, if you take the time reverse of that signal, it means that if you take the x minus t, then even by taking the time reverse, you will get the same signal x of t. So there will be no difference in the symmetry about the even after taking the minus of that signal as well. So this is called even signal, and it is odd if you put minus t. You take the time reverse signal, then in the result you will get minus x of t. It means that both of them will be equivalent. When you take the minus of an original signal, then it can become equal to x of minus. So this is an odd signal. So this is for the continuous case. Similarly, for the discrete time signal, if it is even when if you take the x of minus n, then you will get the equal to x of n. So there is no difference between x of minus n and x of n. Similarly, for odd, if you take the x of minus n, then it can only be equal to x of n by multiplying by the negative with negative to this signal. Now let's discuss an example of even and odd signals. First of all, uh, any signal in the universe can neither be even and odd at the same time, but the possibility is that all zero signal is both even and odd. So any other signal can't be both even and odd, but maybe neither. The following simple example illustrates these properties. So first of all, if you see that if we have a signal x of t which is given t square minus 4t, it's an even signal. How it is an even? Look at this. If you put the if you see this part, time is increasing like the positive side. So if you take the square, then it will improve in this way. It will go in this way for each time value because 40 is a constant value. Similarly, it is for the negative minus t side for this one, because minus t, if you put the minus t, so minus t square will become again t square, right? So this is an even signal, right? Equals to t square. For our signal, minus zero point 0.1 t cube. You know that if you put the minus here, it will not become plus because this is cube. So it is an odd. So for this zero point 0.1 t cube, if you see that for positive value, it's going in this way. For negative value, it's going in opposite direction. For even signal, it was different, right? The third one is neither even nor odd. This is an exponential 0.40. Look at this. If you see, it's continuously increasing. So it is neither even nor odd signal. To clearly discuss the concept, you have to remember some points to know that whether it's even and odd signal. You can just guess from their geometry. How you can guess from the geometry that it's even and odd? So graph an even signal is symmetric about the origin. Some examples are of even signals are given below. You would see that this is origin. Origin means the 0 point. It's symmetric, like the shape is as it is going to the positive side, it looks similar to the negative side. Its shape is same as on the positive quadrant and the negative quadrant. If you see, both the signals are symmetric at 2, 3, for example, minus 2 to minus 3, their shape is same. And if it look at the origin, it's 0 to 1 same shape, 0 to minus 1 same shape. This is for the continuous case, and similarly for the discrete case, if you see that it's also symmetric about around the origin. So this is our origin 0. At 1 it's minus 2, at minus 1 it's similarly its amplitude is minus 2. So for 2 it's 2, and for minus 2 it's 2 as well, so on. So this is an even signal. For the odd signal, geometrically the odd signal is anti-symmetric about the origin. And odd signal, another property you must remember, an odd signal must be such that x0 equals to 0. At the 0 point at the origin, it must be 0, right? Look at this. So at the origin, this signal is 0, and it's anti-symmetry. It's increasing here, and for the negative side is decreasing. So it's not symmetric. Whereas for even case, it was symmetric. If it's increasing, other side also increasing as well. So for discrete case, look at the at origin we have a 0 point, at 1 it's 1, whereas at minus 1 it is minus 1 rather than plus 1 amplitude. So they are not symmetric. Look at this is anti-symmetric. Now the other property is very much important, is the decomposition theorem for signals. What is this decomposition theorem? It means that every continuous time signal, x of t can be expressed as x of t is equal to yt plus zt. What does it mean? That if you have any signal x of t, you can express that signal in the terms of even and odd signal as well. So where yt is even signal, for example, this is even term, and zt is odd. So by combining even and odd, you can generate x of t, which is a decomposition theorem. Proof. Let's define yt, which is the even part. You can write the yt as x of t plus x of minus t, right, over 2. So this is a formula you have to remember, that y of t even part you can write as xt original signal st plus x minus t, like the time reverse version of the same signal, divided by 2. It is the even part. So you can calculate the even part by using this equation. And for the odd part, z of t is the odd part of the signal, you use xt minus, this sign is minus here, x minus t over 2. Clearly, you can see that y minus t equals to yt, and if you put, because this is even part, so even we just studied that if you take y minus t, it should be equal to y of t if it is an even, right? We just studied before a while ago. So if you put here minus t, for example, x of minus t, then put x plus x of minus t, so it becomes plus t. So here x minus t plus x of t over 2, it's same as y of t. So y of minus t equals to y of t. Whereas z of minus t, if you put here minus of t, then it will give you minus z of t. It is equivalent to minus z of t, not z of t. So this is odd part. So we can also check that if we add these two, we will get x of t. So terminology, the signal yt is called the even part of xt. This is called the even part of the xt, denoted by usually ev. It means even of x of t. The signal zt is called the odd part of xt, denoted by odd x of t. So this is a decomposition theorem. Any signal, continuous or discrete, right? This is for continuous we discussed, but for any signal either is continuous or discrete, the summary is that we can represent that signal in terms of even and odd parts. We can divide the signal into two parts, y of t, z of t. So this is even and this is odd. And to calculate the even component of a signal, you use this equation, right? And for to calculate the odd component of signal, you use this equation, right? Okay, let's consider an example. For example, you have a signal x of t given e of t. So you have to calculate the even part. So even part E of t plus E of minus t over 2, which by geometric some manipulation, or these are some kind of formulas you have already seen in mathematics, that this term is equal to cos of hyperbola t. So this is a known fact. So we can write this as a cos hyperbola t. And for the odd part, calculating the odd part of E of t, so we have our signal E of t. So E of t minus E minus t over 2, this is equal to sine hyperbola t. Similarly, we can define even and odd parts of discrete time signal. This was for the uh, continuous. So for even and odd part of a discrete, you can write xn plus x minus n over 2. For odd, xn minus x minus n over 2. So it is easily to check that xn equals to xn even plus xn odd. By combining this, you will get xn as well. There are some properties you must remember about the symmetry and addition and multiplication. Sums involving even and odd functions have the following properties. So if you have a sum of even and odd function, they have following properties. The sum of two even function is always even. You must remember, if you have two even functions, for example yt, zt, they are two. If you want to add them, then the summation of that even function will always be even, not odd, right? The sum of two odd function will always be odd. And the third one is that sum of an even function and odd function is neither even nor odd, provided that neither of the function is identically zero. What does it mean? It means that if you add the odd function and the even function, the result will neither odd nor even, but uh, it can be neither, but uh, provided that the neither of the function is identically zero. If one of them is zero, then it can be even and odd. Otherwise, if you sum the even and odd function, it will be neither odd nor even, right? That is, the sum of the functions with the same type of symmetry also has the same type of symmetry. The conclusion is that if you add the two functions with the same type of symmetry means that if they both of them are odd, then in the result you will get the same type of symmetry. It means odd. And if the both of them are even, so in result you will get the same type of symmetry. It's even. It was for sum. Now let's see the product. What happens to the product? Product involving even and odd functions have the following properties. For example, if you have a product of two even functions, then the product output product will be even as well. So if you multiply or the product of a two odd function, here the output will be even, right? This is you must remember, odd even. So product of an even function and odd function is odd, right? So you must remember this one. That is, the product of functions with the same type of symmetry is even. So conclusion is that if you multiply the two functions which have the same type of symmetry, then the result will be even. While the product of function with opposite type of symmetry is odd. For example, if you multiply even and odd, then you will get odd, right? But if you multiply two same functions, then the product will always be even. Or let's discuss some signals. These are some signals which are adopted in the communication systems. So one is the real sinusoidal signal. So what is real sinusoidal signal? As the term mean, real and then sinusoid. This is the combination of two, real and the sinusoid. So for a continuous time, real sinusoid is a function of the form this one. So this x of t is a real and sinusoidal. How it is real? Because a, omega, theta are all real constants, like a here, omega here, and theta. Three of them are real values. There is no imaginary term involved. And it's following the sinusoid, so it's a real sinusoid. Such a function is periodic with fundamental period. So you know that the cos functions and sine functions are periodic functions. So such a function is periodic with fundamental period. They have a fundamental period which is 2 pi by omega. So t equals to 2 pi over omega. and fundamental frequency is omega. Okay, right? So a real sinusoid has a plot resembling that shown below. So this is the real sinusoid plot, A cos omega t plus theta. This theta is nothing else, you know that it's a time shift in the start. If it is 0, it means that it will start from here, right? There will be no delay or no advance. If theta has some value, it can be a delay. For example, 30 degree, theta is 30 degree. It means that you have a delay of a 30 degree. If it's minus 30 degree, then you have an advance of 30 degree. So this theta has nothing to do except the starting point. The other one is the complex exponential. So exponential means exponential signal, and complex means that they involve the complex term. Complex means with the j term, right? This is the complex, right? You know that there are two components, a plus j omega, right? So in this is real part and this is complex part. So they are discussing about complex exponential. So it means that they have this j part, right? So a continuous time complex exponential is a function of the form xt a e lambda t. So they have exponential and a. So where a and lambda are complex constants. So a and lambda both are complex. So that's why they are called complex exponential. Why exponential? Because the e term is involved here. So that's why it's exponential. So a complex exponential can exhibit one of number of distinct modes of a behavior. So they can have a number of different modes. Modes means they depending upon the values of its parameters a and lambda. If you vary the value of a and lambda, so its shape changes, right? So it means that it has different modes of behavior, distinct modes of behavior. For example, as special cases, complex exponentials include real exponentials and complex sinusoids. So complex exponential can include special case. This is a special case that include real exponentials, means the only real, and the complex sinusoid. So both of them are included. So other one is real exponential. What does it mean, real exponential? A real exponential is a special case of a complex exponential, as we discussed in the previous slide. So why it's a special case? Because here only the real terms are involved. Complex, there is no complex terms involved. For example, xt e a e lambda t. So previously we have a and lambda. You know that in the previous this was complex values, but here we have a and lambda are restricted to be real number. As I mentioned, a plus j omega, right? Jb, for example. So we have no, this term is not involved. So only real terms. So a and lambda are real. So that's why they are called real exponential. So real exponential can exhibit one of three modes of behavior depending on the value of lambda. This lambda value impacts the shape of the signal. For example, if lambda is greater than 0, this is the case, right? Lambda is greater than 0, so our exponential is increasing in this way, right? So increases exponentially as t increases. As t increases, so lambda is a constant value. So greater than 0 means it's a positive value, right? So for example, e lambda e a e 2t. So when t increases, the exponential increases. So the function increasing exponentially. If lambda is less than 0, it means minus term this one. So if time increases, then exponential term decreases. So look at this. And other is lambda 0. It means that a is constant. So a is constant. Because lambda 0, e 0 is 0, it means 1. So you will get the constant equal to amplitude. A is a constant term, right? So this is three different cases for real exponentials. The other one is the complex sinusoid. A complex sinusoid, as you know, that sinusoid and with the complex behavior is a special case of a complex exponential. Is a special case. It's a special case of exponential, but with sinusoid term. What is mean where a is a complex, as you know that complex sinusoid, and lambda is purely imaginary. It means that there is a imaginary term, and imaginary means that real part is 0. So real of lambda is 0, and we will have only the imaginary term involved. That is the CT means the complex continuous time complex sinusoid is a function of the form x of t e a e j omega t. So we have only, as I mentioned, that a plus j omega, right? A plus j omega. So if real term is 0, this one 0, so we have only the function j omega. So if you put here, so it's j omega t, right? So xt is equal to a e j omega t, right? Where a is complex and omega is real. So you know that omega is a real number, so that's why. And by expressing a in a polar form, you know that this is a rectangular form a plus j omega. If you express them is in a polar form, so it has a magnitude a and the angle ej theta. So here we have a theta. Theta is a real. And using Euler's identity relation, we can rewrite x of t as this one. X of t a amplitude cos omega t plus theta plus j a amplitude sin omega t plus theta, right? Due to this, because ej theta is equal to cos theta plus j sin theta, right? By using that Euler's identity, we can rewrite this equation as this one, right? Thus, real and imaginary are same except for a time shift. So the real part, if you see, and the imaginary part, if you see from here, they both are same, but there is a time shift. Time shift means because one is cos and other is sine. So they have a 90-degree of shift. Also, x is periodic with fundamental period t is equal to 2 pi over omega and a fundamental frequency omega. So this is a graph of a complex exponential. The graph of real and imaginary have the form shown below. This is real part a cos omega t plus theta, and this is the imaginary part a sin omega t plus theta, right? So if you put different values, you can get this plot. The last is the general complex exponentials. What are they? General complex exponential. General means they are. This is the generalized form of complex exponential. In the most general case of complex exponential, we have xt, a, e, lambda t, we already discussed, and a or lambda are both complex because we are discussing about the complex exponential. Let a equals to a amplitude and the ej theta in polar form, right? And lambda equals to, because they have general, it means it can have a real and imaginary part. So lambda equals to sigma plus j omega, where theta and sigma and omega are real. These are real numbers. Sigma, theta, and omega, they are real numbers, right? And using Euler's relation, we can rewrite as we previously rewrite a cos omega t plus theta plus j a sin omega t plus theta. But here we have an additional term which is e sigma t, right? And e sigma t here as well due to this, right? This sigma. So thus real and imaginary are each the product of real exponential and real sinusoid. So real, they have exponential as well and the sinusoid. Exponential and the sinusoid, both of them are involved here. So one of the three distinct modes of behavior is exhibited by xt depending on the value of sigma. So sigma, if sigma is 0, it means that the exponential term will be 1. So then it will become real sinusoid. Real sinusoid means that it is sinusoid, right? And if sigma is greater than 0, then each are real and imaginary. If, for example, a sigma is greater than 0, so both part real and imaginary terms are each the product of real sinusoid and the growing real exponential. So there will be a product of exponential plus sinusoid, exponential plus sinusoid. If less than 0, are the product of real sinusoid and a decaying real exponential. So this is the general complex exponential writing style. Now let's check how this function looks like. Okay, these three modes of the behavior. This is a mode when sigma is greater than 0. So look at this. These are growing exponential. It's growing in this way, right? It will keep growing. Look at it, start from less and keep growing. And for the sigma equals to 0, it's the only exponential, like the not growing. It's constant, right? So you see that it's a just like a cosine or a sine function. And for the case sigma is less than 0, it's like a decaying exponential. Look at this. This is going down here, This is going down here. So this was our discussion for today. Okay, thank you for listening to this lecture. And for a question answer, there will be a separate Q&A session. The exact date and time will be communicated later on. Thank you very much.